Hello everyone. This is Sister Lindsay Celestine, Assistant Professor, Department of Mathematics from St. Josephs College of Arts and Science for Women. Here we are going to see Cramer Rao inequality. Before going to see the Cramer Rao inequality, we are going to see some basic definitions. The first one is most efficient estimator. Okay, if we consider a class of consistent estimators, okay, then in that there is only one estimator which has a less sampling variance other than the other estimators. So that is called the most efficient estimator. Next one is efficiency. For efficiency we are considering two estimators. Okay, that is T1 and T2. In this T1 is the most efficient estimator with variance V1. That means this T1's variance is less than the other variance. Okay, and T2 is any other estimator. If we want to find out the efficiency for T2, then A is equal to V1 by V2. That means most efficient estimator's variance divided by the any other variance estimator. By this we are finding the efficiency. Then next is minimum variance unbiased estimator. If a statistic T based on samples of size n is such that if we are telling that T is the minimum variance unbiased estimator of gamma of theta, when we have two conditions. One is T is the unbiased for gamma of theta. T that means T is the expectation of this T is equal to this gamma of theta, and this T has the smallest variance among the class of all unbiased estimators gamma of theta. Next, we are coming to the Cramer-Rao inequality. The statement is T is an unbiased estimator, that is, this variance is that means the expectation of this T is equal to gamma of theta of a function parameter. If it is unbiased estimator, then we have to prove the following: variance of T should be less than or greater than or equal to d by d theta gamma of theta the whole square divided by expectation of dou by dou theta log L the whole square. We are taking this expectation of dou by dou theta as I of theta. Okay, so this is we are writing gamma dash of theta by the whole square. Okay, so next we are coming to the result. Before going to prove the result, we have some common assumptions, basic assumptions. Okay, the first one is that theta is the single parameter and it is also the unknown parameter. Then we are taking the continuous random variable, and also we are taking the discrete random variable when on replacing the multiple integrals. Then also we have some regularity conditions. The first one is the parameter space is the non-degenerate open interval on the real line. Second one is for all x and all theta, this derivation dou by dou theta L of x comma theta exists. The exceptional set if any is independent of theta. Then the third one is the parameter theta is independent. If the parameter theta is independent, the range of integration, if the parameter theta is independent in the range of integration, then f of x comma theta, that PDF function is differentiable. If the range is not independent of theta, then f becomes 0. Using that, we are going to have this equation. That means dou by dou theta integral a to b f dx equal to integral a to b dou f by dou theta dx minus f of a comma theta dou a by dou theta plus f of b comma theta dou a by dou theta. Since this a and b are dependent, then these two terms becomes 0. Okay, then we have only integral dou by dou theta integral a to b df dx equal to integral a to b dou f by dou theta into dx. Then the fourth condition is the continuous of uniform convergence of integrals are satisfied. So the differentiation of the integral sign is valid. Next, the fifth one is we have considered I of theta is this one, that is exists and it is positive. Now we are coming to the main result. Let x be a random variable following the PDF f of x comma theta and L be the likelihood function. Okay, so now we are telling likelihood function formula L equal to L of x comma theta, which means product of all the density functions of the random sample of population. And this L is since it is the joint probability function, probability density function, then we are writing probability density function means it should be the density function should be equal to 1. Okay, that density function should be equal to 1. So we are writing integral dx is equal to all the integrals dx1, dx2, etc. Differentiating this with respect to theta, then we have integral dou by dou x. This is joint probability function, so we are doing partial differentiation. So dou by dou theta L dx equal to, if we differentiate this one, since this is constant, it becomes 0. Then we are writing this L dou by dou theta into L as we are representing dou by dou theta log L into L dx. So this is expectation formula, expectation of x is equal to integral x into f of x dx. So using this formula, we are writing this equation as like this. Now we are telling expectation of this term dou by dou theta log L equal to 0. This one we will use in the next slides. Now we are considering another one unbiased estimator as in the theorem statement. Let T, here T is T is not a single value, it is the sample n size sample values. Okay, it is an unbiased estimator. Okay, we know the formula. If it is an unbiased estimator, then the expectation of this t is equal to gamma of theta, and we know the formula of expectation of t. So we are writing like this, integral t into L dx. So we are differentiating this one. So integral t into dou L by, this t is separate value. So it is not different on theta. So we can't differentiate, we'll take as it is. Then this L is the L of x comma theta. So we are differentiating this one. So dou L by dou theta dx equal to this is gamma dash of theta. Okay, then this one we are representing dou by dou theta log L. Okay, log L. So we know this one according to the expectation formula, we are writing like this. Expectation of t into dou by dou theta log L equal to gamma dash of theta. Now we are seeing the covariance. Covariance of x comma y is equal to covariance expectation of xy minus expectation of x into expectation of y. Using that formula, we are writing this. So using from equation 3, we are writing, instead of this, we are writing gamma dash of theta. From equation 1, we already told expectation of this value equal to 0. So this whole term equal to 0, it will be cancelled out. Then we will get only covariance of t comma dou by dou theta log L equal to gamma dash of theta. Now we are considering covariance of x comma y the whole square less than or equal to variance of x into variance of y. So by this we are telling covariance of, instead of x comma y, we have t comma dou by dou theta log L. Okay, so we less than or equal to variance of x into variance of y. So variance of t into variance of y is dou by dou theta log L. So t is the single value, so keep it as it is. Then using the variance of xy formula we are writing, variance of x formula we are writing this one. So variance of x is equal to expectation of x square minus expectation of x the whole square. So expectation of, in the place of x we have dou by dou theta log L. So expectation of dou by dou theta log L the whole square minus expectation of dou by dou theta log L the whole square. And then we know this value is equal to 0 from equation 1. So this will be cancelled out. We get this only this value. So this only we have to prove. We have variance of t, gamma dash of theta the whole square, expectation of dou by dou theta log L the whole square. Log L square we have. So from this we have proved the Cramer Rao inequality, that is variance of t is greater than or equal to gamma dash of theta the whole square divided by expectation of dou by dou theta log n the whole square. Thank you, friends.